Swayam Prabha. Digital India. Educated India.
Welcome to the 7th lesson of module 2 of the course on strength of materials, and this module and the lesson is on analysis of strain part 7. Now, in the previous lesson on analysis of strain, we had looked into some aspects of evaluating strain at a particular point of at a different orientation. If we have axis system oriented differently from the rectangular axis system, then how do you compute the strains with reference to those axis system. Now, in this particular lesson, it is expected once it is completed, one should be able to understand the concept of principal strain and the maximum shear strain at a point and their orientations with respect to the rectangular axis system. One should be able to evaluate strains at a point using transformation equations and Mohs circle of strain. Now, we have already discussed certain aspects of transformation equations, which we are going to discuss further today. Also, as we have looked into in case of stresses, that we can evaluate stress at a point using Mohs circle, we will see that we can evaluate strain as well using Mohs circle of strain. Hence, the scope of this particular lesson includes the recapitulation of previous lesson, and as usual, as we have done in the previous lessons, we will discuss the previous lesson through the answers of the questions that I have posed last time, so that will give you an overview of the previous lesson. Then evaluation of strain at a point for different axis orientation, principal strains, shear strains and their orientation. In fact, with reference to the rectangular axis system, as we look into, the strain at a particular point vary if the axis system differs from the rectangular axis system, which is x, y and z. Now, also we will be looking into the evaluation of principal strains, the evaluation of shear strains and their orientations with reference to the rectangular axis system through transformation equation, which we have dealt with to certain extent last time, and also we will introduce the concept of Mohs circle of strain similar to the line of the Mohs circle of stress as we have discussed already. And then we will look into some examples for the evaluation of strains at a point for plane strain condition. That means, if we know epsilon x, epsilon y, gamma xy, then how to compute strain at a point if we have different axis orientation, and how to compute the principal strains, how to compute the shear strain and their orientations with respect to rectangular axis system. Well, let us look into the questions or the answers to the questions which I had posed last time. Now, the first question which was given was, what is the purpose of transformation equations? Now, that we had derived the transformation equations. Now, we will have to look into that, what is the purpose of this particular equation. Now, as I have told already, that at a particular point, if we are interested to evaluate the strain in terms of the strains which are known in the x direction, y direction and the shearing strain, that is epsilon x, epsilon y and gamma xy, then in this particular point, if we like to evaluate the strain with reference to another axis system which is oriented at an angle of theta with reference to x axis, and let us say this is x dashed and y dashed axis, then what will be the state of strain at this particular point? Will they still be epsilon x, epsilon y, gamma xy, or they will be different? Now, through transformation equation, we try to evaluate the strain at that particular point with reference to different axis system which are x dashed, y dashed in this particular case. So, the purpose of the transformation equations is to evaluate the strain at different orientation with reference to the rectangular axis system x and y. Now, the second question was, how will you derive the value of maximum normal strain? Now, please note here that we are going to find out the value of the maximum normal strain. Now, we had computed the value of normal strain at a particular point when it is oriented at an angle of theta. The axis system is oriented at an angle of theta with reference to x and y. Now, what we need to do is that first the value of the maximum normal strain and at which location that occurs. Now, the transformation equations which I had written down last time, or we had derived, epsilon x, the normal strain in the x direction, is epsilon x cos square theta, epsilon y sin square theta plus gamma xy sin theta cos theta, where theta is the angle which is oriented in an anti-clockwise form with reference to the x axis, and thereby epsilon x dashed can be written as epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 times cos 2 theta plus gamma xy sin 2 theta by 2. And also, if we substitute for theta as theta plus 90, then this gives us the value of epsilon y, which is epsilon x plus epsilon y by 2 minus epsilon x minus epsilon y by 2 cos 2 theta minus gamma xy by 2 sin 2 theta. And the shearing strain with reference to x dashed y dashed axis, which is gamma x dashed y dashed, we have written in terms of gamma x dashed y dashed by 2, which is equals to minus epsilon x minus epsilon y by 2 sin 2 theta plus gamma xy by 2 cos 2 theta. Now, let us look into that if we have to find out the maximum normal strain. Now, this is the normal strain epsilon x dashed which is acting in the x direction. Now, what we need to do now is to find out the value of the maximum normal strain. Now, to do that, if we take the derivative of the strain with respect to theta, we can get the value of the angle at which the maximum normal strain will be oriented. So, let us look into that aspect first. Now, epsilon x dashed, as we have noted down, is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta. Now, if we take the derivative of this with respect to theta, this is equals to epsilon x minus epsilon y by 2 minus 2 sin 2 theta plus gamma xy by 2 cos 2 theta. This 2 gets cancelled. So, this is now for the maximizing the normal strain, this is equals to 0. So, 0 is equals to epsilon x minus epsilon y by 2 sin 2 theta with a minus sign here plus gamma xy cos 2 theta. Now, this gives us that value of tan 2 theta is equals to gamma xy by epsilon x minus epsilon y. Sorry, this 2 goes off. This 2 gets cancelled. So, epsilon x minus epsilon y sin 2 theta. So, tan 2 theta is equals to gamma xy by epsilon x minus epsilon y. Now, let us call this angle with the suffix p for the maximum normal strain we generally designate as principal strain. As we had done in case of stresses, that maximum normal stress is designated as principal stress, the maximum normal stress and the minimum normal stress as principal stresses. Here the strain values, the maximum normal strains we call as principal strains, and their orientation angles are denoted with as theta p. Now this 2 theta p, now this particular equation has two solutions. One is 2 theta p and tan of 180 plus 2 theta p is also the same value. So we will have two angles, one is theta p, another one is 90 plus theta p in the physical plane. So this gives us the orientation or the direction along which the normal strain will be maximum. Now if this is the orientation along which normal strain is the maximum, then what is the value of the corresponding normal strain, which is the maximum normal strain? Let us look into that. Now we have obtained that tan 2 theta p, this is equals to gamma xy by epsilon x minus epsilon y. So if this is the angle 2 theta p, then this is gamma xy and this is epsilon x minus epsilon y, and let us call this hypotenuse as r. So r is nothing but equals to root of epsilon x minus epsilon y square plus gamma xy square. So cos of 2 theta p is equals to epsilon x minus epsilon y by r, and sine of 2 theta p is equals to gamma xy by r. Now if we substitute the value of cos 2 theta p and sine 2 theta p in the expression for epsilon x dash, that will give us the maximum value of the normal strain. Let us call that as epsilon 1, and that is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2. In place of cos 2 theta p, we write epsilon x minus epsilon y by r plus gamma xy by 2, and in place of sin 2 theta p, we write gamma xy by r. Hence this is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y square plus gamma xy square divided by twice r, and the numerator epsilon x minus epsilon y square plus gamma xy square, this is nothing but equals to r square. This we write as r square. So this r square gets cancelled, so it becomes r by 2. So this is basically equals to epsilon x plus epsilon y by 2 plus this is r, which is root of epsilon x minus epsilon y square plus gamma xy square, half of that. And if we take these two inside, then this can be written as epsilon x plus epsilon y by 2 plus root of epsilon x minus epsilon y by 2 square plus gamma xy by 2 square. So this is the value of the maximum normal strain. Well, this is the value of the maximum normal strain that is acting on at that particular point. Now we can, if we look into the expression for the shear, now here if we look into that, the shearing strain gamma x dash y dash is given as this. Now we have already looked into that the angle at which the maximum normal strain occurs is tan of 2 theta p, which is equals to gamma xy by epsilon x minus epsilon y. Now, if in this particular expression for shearing strain, if we substitute for gamma x dash y dash as equals to 0, this expression leads us to the value of tan 2 theta as equals to gamma xy by epsilon x minus epsilon y. So, that indicates, so this expression indicates that if this gamma x dash y dash is substituted as 0, then tan 2 theta is equals to gamma xy by epsilon x minus epsilon y. This indicates that the angle at which the maximum normal strain occurs, there the shearing strain is 0. As we had seen in case of stresses, that the plane along which the maximum normal stress acts, at that particular plane the shearing stress is 0. So, in similar line here, where the point where or the orientation at which we get the maximum normal strain, which we are calling as principal strain, at that point the and corresponding to that in that element the shearing strain is 0, where the maximum normal strain occurs. So, this we have seen now that the tan 2 theta p is equals to gamma xy by epsilon x minus epsilon y, and corresponding to the angle of 2 theta p, we get the value of epsilon 1, which or epsilon max, we call this as epsilon max. Now, if we substitute as 180 degree plus 2 theta p as the other angle and substitute for cos and sin, we can get the value of epsilon 2. So, the epsilon 1 or epsilon 2, the maximum and the minimum normal strain, this is the maximum and the minimum normal strain, and these are given as epsilon x plus epsilon y by 2 plus minus, for plus is for epsilon 1 and minus is for epsilon 2, as square root of epsilon x minus epsilon y by 2 square plus gamma xy by 2 square, as we have derived just now. Now, the third question was that how will you find the value of maximum shear strain at a point for plane strain condition. Now, let us look into this particular answer, that how we are going to compute the value of maximum shear strain. Now, as you have seen that the shearing strain at any orientation which is at an angle of theta with reference to x axis, which is oriented at an angle of theta, which is our x dash, gamma x dash y dash corresponding to that particular direction is epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta plus gamma xy by 2 cos 2 theta. Now, if we take the derivative of that gamma x dash y dash by 2 is equals to minus epsilon x minus epsilon y by 2 sin 2 theta plus gamma xy by 2 cos 2 theta. Now, we take the derivative of this with respect to theta, and eventually this gives us epsilon x minus epsilon y by 2 times minus 2 cos 2 theta and minus cos 2 theta minus 2 sin 2 theta minus 2 gamma xy sin 2 theta by 2, and if we set this as equals to 0, d gamma xy d theta as 0, then we get the value of tan 2 theta again from this expression, which is equals to epsilon x minus epsilon y by gamma xy. Now, in the previous case, when we had evaluated the maximum normal strain, we had the value of angle 2 theta p was gamma xy by epsilon x minus epsilon y, and in this particular case we are getting, when we are taking the derivative of the shearing strain with respect to theta, we are getting the value of the angle which we are calling as the angle for the shear theta s, tan 2 theta s is equals to epsilon x minus epsilon y by gamma xy. So, we can in general write that tan 2 theta s is nothing but equals to minus 1 by tan 2 theta p, which is equals to minus cot of 2 theta p, and this we can write as tan 90 plus 2 theta p. So, 2 theta s is equals to 90 plus 2 theta p. Hence, theta s is equals to 45 degree plus theta p. This shows that the angle at which the shearing strain is maximum, that orientation is 45 degree with respect to the orientation with reference to the principal axis strain. So, the direction along which the maximum normal strain occurs, where we get epsilon 1, which is the maximum epsilon x, if we orient by another 45 degree, the axis which we will get corresponding to that, we will get the values of maximum and minimum shear strain. Now, if we take the values of tan 2 theta s as we have obtained, now this is the angle 2 theta s. Now, this is gamma xy and this is minus epsilon x minus epsilon y. So, this is tan 2 theta s, which is equals to minus epsilon x minus epsilon y by gamma xy, and then the value of r is equals to root of epsilon x minus epsilon y square plus gamma xy square. Hence, the value of cos 2 theta s is equals to gamma xy by r, and sin 2 theta s is equals to minus epsilon x minus epsilon y by r. Now, if we substitute the values of cos 2 theta s and sin 2 theta s in the expression for gamma, which is gamma x dashed y dashed by 2 is equals to minus epsilon x minus epsilon y by 2 sin 2 theta plus gamma xy by 2 cos 2 theta. Now, in this particular expression, if we substitute for cos 2 theta and sin 2 theta in terms of gamma xy by r and epsilon x minus epsilon y by r, we get this as epsilon x minus epsilon y square by twice r, epsilon x minus epsilon y square by twice r plus gamma xy square by twice r, and eventually again epsilon x minus epsilon y square plus gamma xy square is r square. This is equals to r by 2, and hence the value of gamma max, gamma x dashed y dashed, when we are substituting for sin 2 theta cos 2 theta in terms of cos 2 theta s and sin 2 theta s, then the maximum value of gamma max can be written as equals to epsilon x minus epsilon y by 2 square root of epsilon x minus epsilon y by 2 square plus gamma xy by 2 square. So, similarly, as we have done in case of the maximum normal strain, we had two angles 2 theta p and 180 degree plus 2 theta p. Here also we have two angles 2 theta s plus 180 plus 2 theta s, and if we substitute corresponding values, we will get the value of minimum shearing strain, and the magnitude of the shearing strain maximum and minimum value is equals to epsilon x minus epsilon y by 2 square plus gamma xy by 2 square, and maximum is plus of this and minimum is minus of this. So, plus minus of this is why it is written as plus minus square root of epsilon x minus epsilon y by 2 square plus gamma xy by 2 square. This is the value of the maximum and the minimum shearing strain corresponding to the plane strain condition. Well, now that we have evaluated the strain at a point if the reference axis is oriented at an angle of theta with reference to rectangular axis system x and y. We have seen how to compute the value of the maximum normal strain, which we have called as principal strain. We have seen how to compute the value of the maximum shearing strain and the orientations of the principal strain and the shearing strain through the angles theta p and theta s. Now, as we did in case of stress evaluation at a point, we had calculated the values of the maximum normal stress, which we had called as principal stress. We had calculated the maximum shearing stresses and their orientations with reference to the rectangular axis system. Now, as we did in case of stress evaluations, we had evaluated at any orientations through transformation equations. Also, we had evaluated stresses at a point at any orientation through Morse circle of stress. Now, in case of strain, as so long we have calculated the values at a point at different orientation, the normal strains and the shearing strains, the maximum value of the normal strains, the principal strain and the maximum shearing strain through the use of transformation equations. Now, we can solve or we can find out the strain at any orientation at a particular point using Morse circle of strain. Now, we will look into the concept of Morse circle of strain. Now, before we get into that, let us look into that how do we really look into the sign conventions of different strain components. Well, as we have seen that positive normal strain, that norm is basically is the elongation per unit length. When we have said epsilon x is the strain in the x direction, we referred that extension or the elongation in the x direction. Likewise, when we are talking about the positive strain in the y direction, it is elongation in the y direction, and when we are talking about the negative strain both in the x and y direction, basically they are under compression. So, positive normal strain is the elongation per unit length and compressive normal strains are considered as negative. Now, in case of shear strains, this is little different than the normal strain. They are positive when angle decreases and negative when angle increases. Now, this will be probably will be more clearer if we look into the figures. Now, based on this particular definition of positive and negative shears, we can say that positive shear stress cause positive shear strain and the vice versa. So, let us look into the figures and then it will be more clearer. Now, in these particular figures, if you look into that, let us say that this is an element, small element of length dx, and at a point where the member is undergoing strain. Now, this is the extension, and if the strain in this direction is epsilon x, we write this as epsilon x dx. This is the extension and this is elongation and we call this as a positive strain. Now, again in this particular element, this is dx and this is dy. Now, in this particular case, the compression of this element is denoted by this dot line, and this is again epsilon x dx, but it is gone in the opposite direction or it has compressed. So, here in this particular case epsilon x is negative. Now, in this particular case here this is again dx and this is dy. Now, in the y direction this is elongated, the element is elongated and it has taken this particular position. So, this extension is equals to epsilon y times dy, and here since it is elongation we call this epsilon y as positive. Now, in this particular figure again this element length here is dx, this is dy. Now, here this part has come to this particular position wherein again the compression of this element is equals to epsilon y dy, but since it has undergone compression, so epsilon y here is negative. So, that is how we define the positive and negative normal strain. Now, in case of shearing strain, Now, as we said that when angle decreases, then so this was the position x and y. Now, from this x and y position, this was the element dx and dy. Now, here this is oriented in this particular form, thereby the angle which was 90 degree before now is getting reduced, the angle is reduced, and hence this particular shearing strain is called as the positive shear strain. And here in an anti-clockwise direction it is moving in this form, here in a clockwise direction it is moving in this position, and this we call as gamma xy by 2 and gamma xy by 2. Now, if you remember last time when we were computing the value of gamma x dash y dash, which was the summation of two quantities alpha and beta, and alpha was the orientation of x axis in the position OA and beta was the orientation of y axis along OB, and sum of alpha and beta gave us the value of the shearing strain gamma x dash y dash. Now, here we are the position from let us say OA and OB is moving to this position, and thereby the angle is decreasing, and we call this shearing strain total gamma xy by 2 plus gamma xy by 2, which is gamma xy, as the positive shearing strain, and this is the position that this particular element is going to take because of the shearing strain. Now, if we remember that we had discussed about the positive shear. Now, shearing stress, if we draw in this particular element, now direction of positive shear stress is this on this face, and on this face it is downwards, on this face it is in this direction, on this face it is in this direction. Now, this positive shear, as we had taken in case of the construction of the Mohr cycle, if you remember that this upward shear along with this complementary shear causes an anti-clockwise rotation, and this shear along with the complementary on the other face causes a clockwise rotation, and this anti-clockwise rotation we had taken as positive, the clockwise one we had taken as negative. Now, this positive direction of shear tries to deform the element in this direction. This direction of positive shear tries to deform the element in this direction, and that is why this is positive strain. Now, in contrast, if we look into the strain which is a negative one, here the angle between the two axes OX and OY was 90 degree. Now, because of the strain it has increased. Now, this increase is due to the shearing strain, and this we define as the negative shear strain. So, this is again gamma xy by 2 and this is gamma xy by 2. Now, please note that in the previous case this movement was in an anti-clockwise direction, in this particular figure it is in a clockwise direction, and here it was in a clockwise direction, here it is in anti-clockwise direction. So, clockwise anti-clockwise movement we will in Mohr circle will consider as positive as before, and clockwise direction we will consider as negative as before. Now, this is the configuration which shows that this particular element which was of length dx and dy in the initial stage undergoes deformation in the x direction, undergoes deformation in the, this is deformation in the x direction, this is the deformation in the y direction, and also it has shearing strain. So, the final position after undergoing the epsilon x, epsilon y and gamma xy, this is the position that it is going to take. So, this particular configuration corresponds to epsilon x, epsilon y, gamma xy, where all are positive, while all are positive. Now, in this particular figure again, if we look into this particular element which is originally again of length dx and dy, now it undergoes strain, but in the opposite direction or gets compressed. So, this is the negative epsilon x dx, and again here in this particular direction this is the deformation, it gets compressed, which is epsilon y dy, and it has a negative shearing strain, and because of that the angle increases, and when we combine all three strain it takes the shape in this particular form. So, this particular configuration is corresponding to epsilon x, epsilon y, gamma xy, where all three quantities are negative. So, this is the sign convention which we follow, and we will be following this convention while plotting the Mohr cycle for the strain. Now, exactly in the similar line as we did in case of stress evaluation, we will be computing the strain identically using the Mohr cycle of strain. Now, let us look into how we do that particular job. Now, here let us say we have strain at a point, or this is an element, small element, where the lengths are dx and dy, and it has undergone strain epsilon x, epsilon y and gamma xy, and from this configuration you can make out that it's all quantities are positive, epsilon x is positive, epsilon y is positive and gamma xy is positive. So, if we take these quantities, now we can compare our relationship with the stresses. Now, in case of a stress at any orientation x dash, it was written as a function of sigma x, sigma y and tau xy. Now, here in contrast to this, the normal strain epsilon x dash, we are writing in terms of epsilon x, epsilon y and gamma xy by 2. Now, this is, if you look into the expression for epsilon x dash and sigma x dash, you will find sigma x dash is equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Sigma x dash is equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Now, in case of epsilon x dash, we have epsilon x dash is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta. So, in place of tau xy we have gamma xy by 2, in place of sigma x we have epsilon x, and in place of sigma y we have epsilon y. Otherwise, the expression is identical. Now, let us find out that how do you compute the strains at any orientation with reference to this x and y at a particular point. If we know the strain at a particular point, which is given by epsilon x, epsilon y and gamma xy, we are interested to find out strain at that point, which is at any orientation which is at an angle of theta in an anticlockwise form with respect to x. So, we need to find out epsilon theta and gamma also in that orientation in theta. Now, as we did before, now the x axis, instead of last time for stresses we had written down for sigma, here we write this strain for epsilon, and the y axis, instead of tau we write now this as gamma by 2 axis, and this is the origin. Now, from here if we plot the value of epsilon x and gamma xy by 2, then we get one point on this plane which we call as a Mohr's plane. Also, epsilon y and gamma xy by 2. Now, if you remember that gamma xy by 2, when we were looking into the sign convention, from x it is oriented at an angle of gamma xy by 2 in the anticlockwise form, which we are calling as positive, and in the y direction it is oriented again by gamma xy by 2 in the clockwise direction, which is the opposite to this. So, if we have plotted gamma xy in this particular position, now here we take epsilon y and gamma xy. So, this is the distance which is epsilon y, and this is gamma xy by 2. and this is the distance. This point is at a distance of epsilon x from origin, and this is gamma xy by 2. Now, if we join these 2 points, this 2 points when it crosses the epsilon axis denotes the center of the circle, and this line is the diameter of the Mohr circle. Now, if we look into this particular triangle and this particular triangle, now this is equals to this is equals to this, hence this is equals to this, and so the distance from here to here, this particular distance is divided equally by this particular point. Now, from O to A, the distance is epsilon x. From O to B, the distance is epsilon y. So, the distance AB is equals to epsilon x minus epsilon y, and the central point from O, if we call this as O dash. So, O dash A or O dash B, O dash A equals to O dash B is equals to epsilon x minus epsilon y by 2. Hence, the distance of the center from the origin, this particular distance is equals to O A minus A O dash. The distance O dash is equals to O A minus A O dash. Now, O A is equals to epsilon x. So, this is equals to epsilon x minus A O dash is equals to epsilon x minus epsilon y by 2. So, this minus epsilon x minus epsilon y by 2 gives the value of epsilon x plus epsilon y by 2. So, this distance from the origin to the center, the distance is epsilon x plus epsilon y by 2. Now, if we look into this particular circle, if we take this O dash as the center and O C as the radius, and if we plot a circle, we eventually get the circle which we call as a Mohr circle for strain, wherein the axis in the x direction is corresponds epsilon, and the axis in the y direction corresponds to gamma by 2. Now, from this we can compute. Now, this is the point which represents the value of the maximum normal strain, and this we designate as epsilon 1. This is the value of the minimum normal strain, and this we designate as epsilon 2. Also, this is the value which gives us the maximum value of the shearing strain, and this is the maximum shearing strain, which is equals to the radius of this particular circle. So, if we know epsilon x, epsilon y and gamma xy, then we can compute the value of epsilon 1, compute the value of epsilon 2 and the shearing strain. Now, the value of epsilon 1, from this you can make out from this value of epsilon 1 will be equals to, from this particular diagram, is equals to the distance O dash plus the radius. So, O dash plus radius, and the value of the radius if we look into, now from this particular diagram O dash A and C, from this particular triangle C A dash is equals to gamma xy by 2, O dash A is equals to epsilon x minus epsilon y by 2, this distance is epsilon x minus epsilon y by 2. So, the distance CO dash, which is the radius, is equals to root of epsilon x minus epsilon y by 2 square plus gamma xy by 2 square. So, if value of epsilon 1 is equals to O dash, which is epsilon x plus epsilon y by 2 plus root of epsilon x minus epsilon y by 2 square plus gamma xy by 2 square. So, this gives us the value of epsilon 1, which we have seen already through transformation equation, and epsilon 2 will be O dash minus the value of the radius. So, this is once we substitute this as minus, we will get the value of epsilon 2, and this is the radius which is equals to the plus and minus gives us the value of the shearing strain. So, using Mohr cycle of strain, again we can compute the values of the principal strains epsilon 1, epsilon 2 and the maximum value of the shearing strain. Well, let us look into how do we plot the Mohr cycle of strain if we know the normal strain components epsilon x, epsilon y and gamma xy. Now, for this particular element at a point, now we have the values of this element as dx dy and the strains in the x direction as epsilon x, y in the y direction as epsilon y and the shearing strain as gamma xy. Now, if we know these components, now our job will be to evaluate the strains at this particular point, the maximum normal strains, the maximum shearing strain and their orientation, and also to locate at any orientation, say for example, if we have a set of rectangular axes which is oriented at an angle of theta with reference to x and y axis, what are the values of the strain corresponding to that orientation, that also can be evaluated in, through the Mohr cycle. Now, let us look into that if we know the value of epsilon x, epsilon y and gamma xy at a particular point in a plane strain condition, then how we can extract the other informations using Mohr cycle of strain. Now, as we had discussed in case of stresses regarding the direction of the axis, remember that we said that this is the positive x direction in which we call this as epsilon. Now, the gamma by 2 in the y we put in the downward direction as positive. The reason behind this was that if we are interested to evaluate strain at a particular direction which is oriented at an angle of theta in the anticlockwise direction, we can keep the same orientation of angle anticlockwise in the Mohr's plane, and to make this compatibility we consider the direction of gamma in the downward direction. If we consider the gamma positive in the upward direction, then this orientation of anticlockwise in the physical plane will be clockwise in case of the Mohr's plane. Now, to keep the parity between the physical one and the Mohr's plane, we keep the axis direction as positive for epsilon on the right hand side and gamma by 2 in the downward y direction. Now, assuming that the normal strain epsilon x is greater than the normal strain epsilon y, now we know epsilon x, epsilon y and gamma xy. So, we choose a point say epsilon x and gamma by 2, and this is a point on the Mohr's plane. Another point we get corresponding to a value of epsilon y and correspondingly the gamma by 2. So, this distance is epsilon x and this is gamma xy by 2, this is epsilon y and this is gamma xy by 2. Now, if we join these 2 points, it crosses the epsilon axis at this particular point, and this is the diameter of the Mohr cycle and this is the center of the Mohr cycle. Now, with this, if we plot the circle, we get the Mohr cycle of strain. Now, corresponding to this particular circle, the value of the maximum normal strain is this, which we have denoted as epsilon 1. The minimum normal strain is this, which we have denoted as epsilon 2, and the value of the maximum shearing strain, positive shear strain is this, and value of negative shear strain maximum or the minimum shear strain is this. Now, this is the point which denotes the maximum normal strain epsilon 1, and this particular point is oriented at an angle of 2 theta p with reference to this. Now, this is our reference line where epsilon x and gamma xy occurs. So, from this particular reference line, let us call this as OA. If we orient by an angle of 2 theta p, then we get the position for the maximum normal strain, and then if we orient from this position, from the position of the maximum normal strain by 180 degree, then we get the position for minimum normal strain. So, these are the values of epsilon 1 and epsilon 2, and this is the angle which gives us the value of maximum normal strain, which is twice theta p in the Morse plane, and in the physical plane it will be theta p. Now, if we are interested to compute the strain at any orientation which is at an angle of theta with reference to x, then we plot an angle 2 theta from this particular reference line, and if we go in an anticlockwise direction, then if this is the line which represents 2 theta, then this particular point gives us the value of the corresponding normal and the shearing strain. So, this is the value of epsilon, the normal strain at theta, and this is the corresponding value of gamma by 2, gamma theta by 2. And if we go in the opposite direction, diametrically opposite point, this will give the value of epsilon y, epsilon theta or epsilon theta x and epsilon theta y, and correspondingly this value is gamma theta by 2. So, that is how now in this particular plane this theta is oriented at in anticlockwise fashion with theta. So, here also in the Morse plane we go in the anticlockwise direction by 2 theta to locate that particular orientation in the Morse plane, and that is why we consider the direction of epsilon axis and gamma axis in this form, so that this compatibility between the orientation is maintained. And also if you note that this is the plane where this is the orientation along which the maximum and the minimum shear strains are occurring, and they are with reference to this particular reference plane will be at an angle of this is minus theta s, and from here again if we orient by 180 degree we will get this. Now, from theta p, this is the position of the maximum normal strain, and this is the position of the maximum shearing strain, and these two make an angle of 90 degree in the Morse plane, and hence these two directions makes an angle of 45 degree in the physical plane, that we have seen through the transformation equations. So, what we observe here is that the set of transformation equations as we have derived for evaluating strain components at any orientation with reference to the rectangular axis system xy corresponding to the plane strain condition epsilon x, epsilon y and gamma xy, we can achieve the similar results through this Morse cycle of strain as we have observed in case of the Morse cycle of stresses before. Well, now having looked into this, let us look into the problem example, that if we know the state of strain at particular point, then how do you compute the values of the other strains at a particular angle or the principal strain. Now, the state of plane strain at a point in a body is given by epsilon x as this positive, epsilon y as this positive, and gamma xy also is positive. Now, determine the strain components if the axes are oriented at an angle of 30 degree with reference axis in anti-clockwise direction, and also determine the principal strains. Now, if we like to compute the values corresponding to the given values, we have epsilon x as equals to 340 into 10 to the power minus 6, we have epsilon y as equals to 110 into 10 to the power minus 6, and we have gamma xy as equals to 180 into 10 to the power minus 6. Now, from the transformation equations we know epsilon x dash, which is at 30 degree in this particular case, is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 times cos 2 theta plus gamma xy by 2 sin 2 theta. Now, if we substitute, theta is 30 degree, so 2 theta is 60 degree. If we substitute these values, epsilon x is 340, epsilon y is 110. So, this gives us a value of 225 into 10 to the power minus 6 plus 115 into 10 to the power minus 6, and cos 60 is half, plus gamma xy by 2 is 90 into 10 to the power minus 6, and sin 60 is root 3 by 2, and this if you compute, it comes as 360.44 into 10 to the power minus 6. So, that is the value of epsilon x along the direction of which is oriented at 30 degree with reference to the x direction. Now, correspondingly epsilon y dash is equals to epsilon x plus epsilon y by 2 minus epsilon x minus epsilon y by 2 cos 2 theta minus gamma xy by 2 sin 2 theta, and if we substitute these values, this will come as 89.36 into 10 to the power minus 6. So, if we add these two, if we add the values of epsilon x dash plus epsilon y dash, this is eventually will be approximately equals to 450. It should be ideally equals to 450 into 10 to the power minus 6, which is equals to epsilon x plus epsilon y. This we have seen earlier. Now, the value of gamma x dash y dash, the value of gamma x dash y dash by 2 is equals to minus epsilon x minus epsilon y by 2 sin 2 theta plus gamma xy by 2 cos 2 theta, and this is equals to we will get as minus 54.6 if we substitute the values to the minus 6, which gives us the value of gamma x dash y dash as twice of this, which is equals to 109.2 into 10 to the power minus 6, and this is negative. So, you see initially we had the element which is in this form, and we had a strain which is positive in the x direction, we had strain which is positive in the y direction. So, this is the positive strain, and then epsilon gamma xy also is positive, which means the angle is reducing, which is in this form. So, this is the position of the element, and in this particular case when we are computing the strain at 30 degree, we have epsilon x dashed as positive, we have epsilon y dashed as positive, we have gamma x dashed y dashed as negative, and hence if we plot that, you can get the configuration corresponding to that particular element. Well, we will deal with this in the next class. Well, now the next problem is that solve the same problem as we have given in one, but using Mohr circle of strain, compute the principal strain direction and maximum shear strain. Now, the next example is that an element of material in plane strain is subjected to strains of these. We got to evaluate the principal strain and the shear strains, and also strain at an angle of 75 degree. The fourth problem is that strain at a point for an element are given by these values. We will have to determine the principal strain and maximum shear strain using Mohr circle of strain. Well, this particular lesson included the concept of plane strain at a point and for different orientation of axis system, concept of principal strains, shear strain and their orientation using transformation equation and Mohr circle, and examples to evaluate strains at a point using transformation equation and Mohr circle. And look into this question, what is the value of shear strain where normal strain is maximum, what is the value of normal strain where shear strain is maximum, and what is the relationship between the orientation of maximum shear strain to the orientation of maximum normal strain. Thank you very much.